Welcome to Unit 3, Meteorology. Within this unit, we will discuss and explore the composition of our atmosphere as well as the various properties within the atmosphere that affect global climate and local weather patterns. As we learned last unit, the Earth formed approximately 4.6 billion years ago. The early atmosphere was most likely hydrogen and helium and would have been stripped away by solar winds. The secondary atmosphere was formed as a result of volcanic outgassing. The gases that were emitted were probably very similar to the gases released by volcanic activity today, creating an atmosphere that was most likely nitrogen, carbon dioxide, water vapor, but absolutely no oxygen. At this point, early Earth now has plenty sunlight, water, and carbon dioxide. Using your previous knowledge of biology, what process can you think of that would use these natural ingredients? Photosynthesis. Early life on Earth changed the atmosphere. With the evolution of the first cellular organisms, a blue-green algae called cyanobacteria, they began to use the gases in the early atmosphere. These organisms would use the plentiful carbon dioxide and in return would produce oxygen as a waste product. So with photosynthetic life using some of the carbon dioxide and producing oxygen, where did the rest of the carbon dioxide go? Most of the carbon dioxide that was present in our early atmosphere was eventually deposited into our oceans. These processes allow the atmosphere to evolve and become more suitable for life. Our present-day atmospheric composition consists of 78% nitrogen, 21% oxygen, very small amounts of carbon dioxide, an ozone layer, which is a form of oxygen that combines 3 oxygen atoms into each molecule, and if we didn't have the ozone to filter out most of the ultraviolet radiation, our planet would become inhabitable for many living organisms. And there is also water vapor present. Water vapor would vary daily between 1% and 4%. It is the source of all clouds and precipitation. And like carbon dioxide, water vapor absorbs heat given off by the Earth. This leads us to discuss how our atmosphere compares to other planets. When we look at our solar system, most of the planetary bodies and even some moons have atmospheres that surround them. Let's take a look at how gases, temperature, and pressure compare to our neighbors. Venus, one planet closer to the Sun from the Earth, has a very dense atmosphere that is mostly carbon dioxide and has a very strong greenhouse effect, trapping enormous amounts of solar radiation between the surface of the planet and its cloud cover. This causes the surface of Venus to reach approximately 890 degrees Fahrenheit. The immensely dense atmosphere on Venus causes the air pressure at the surface to be 1,305 psi. Psi is the abbreviation for pounds per square inch. Let's think about this. For every square inch, and let's just think of a Starburst candy, which is slightly smaller than a square inch. For every square inch on Venus, there is 1,305 pounds of air pressing down. If you were able to stand on Venus's surface, you would be crushed like a soda can. On Mars, one planet farther from the Sun, average temperatures only reach a high of -64 degrees Fahrenheit. The atmosphere on Mars is very thin and, like Venus, mostly carbon dioxide. A thin atmosphere will allow for low air pressure. Average air pressure on Mars is only 0.15 psi, and if you were able to stand on Mars's surface, the lack of air pressure would cause you to explode. On Earth, Earth is the only planet that has an atmosphere that is suitable for supporting life. Earth is the only planet that has oxygen and liquid water, which is essential for all living organisms. On Earth, the average temperature is 62 degrees Fahrenheit and the average air pressure is 14.6 psi. It also contains an ozone to filter out harmful solar radiation. Now, looking at this comparison, Venus is just too hot, Mars is just too cold, and because of all the conditions being just right on Earth, it has earned the nickname the Goldilocks planet. The greenhouse effect occurs naturally and is essential to maintain a comfortable temperature on Earth. But human activity, in particular carbon dioxide emissions from cars and industrial plants, is drastically increasing the concentration of greenhouse gases. Our ozone layer absorbs ultraviolet radiation, which has damaging effects on human and animal tissue. But chlorofluorocarbons, known as CFCs, that are used in industrial processes, refrigeration, and air conditioning destroy that ozone layer. Geologically, volcanoes and meteorite impacts can add an abundance of gases and dust into our atmosphere. So why should we care? Human activity is drastically increasing the concentration of greenhouse gases. As a consequence, the average temperature on Earth is increasing. This is called global warming, which leads to melting glaciers and polar ice caps and ultimately global climate changes. Destruction of the ozone layer as a consequence of human activity can be reversed by reducing CFC usage, especially in developed countries. We have no control over geologic activity, but added dust to our atmosphere from volcanic activity can have a cooling effect, changing weather patterns. Earth's atmosphere is divided into 5 main layers. The layers are characterized by changes in altitude, temperature, and air pressure. Altitude is the height above the Earth's surface. The atmosphere rapidly thins as altitude increases until there are too few gas molecules to detect. So atmospheric pressure, the weight of the air, decreases with increased altitude. The force of gravity keeps most air molecules near the surface of the Earth. The temperature of each layer will alternate between increasing and decreasing due to the specific characteristics of each layer. The troposphere is the lowest layer of the atmosphere and rises to approximately 12 kilometers above the surface of the Earth. The upper boundary of the troposphere is called the tropopause. Almost 80% of the mass of the atmosphere is concentrated in the troposphere. Temperatures will decrease with increased altitude at a rate of approximately 6.5 degrees Celsius per kilometer. This layer contains the most water vapor, and all of Earth's weather will occur within these first 12 kilometers. Something to think about. When we use airplanes to travel, we are flying within the troposphere. As we move farther away from the surface of the Earth, the second layer of the atmosphere is characterized by clean, dry air. It is the stratosphere. It reaches an altitude of right around 50 kilometers, with temperatures steadily increasing with altitude due to the ozone layer absorbing ultraviolet radiation and releasing some as heat. The boundary between the stratosphere and the next layer is called the stratopause. The third layer of the atmosphere is the mesosphere. It rises approximately 80 kilometers above the surface of the Earth, with temperatures decreasing with increased altitude. The top of the mesosphere is the coldest region in the atmosphere, reaching almost negative 95 degrees Celsius at the top. When you make a wish on a shooting star, you are actually wishing on a meteor that has entered Earth's atmosphere and is burning up in the mesosphere as a result of friction with air molecules, creating that bright streak of light. The thermosphere is the fourth layer from the surface of the Earth and extends to approximately 500 kilometers in altitude. Temperatures will begin to increase with increased altitude as atoms are being accelerated by sunlight. This layer is extremely thin with very few molecules, composed mainly of hydrogen and helium gases. The thermosphere is also affected by solar events. disrupting radio transmissions, and near the poles create the beautiful auroras as the charged particles enter the atmosphere. The exosphere is the outermost layer of Earth's atmosphere, where there is no clear boundary between the exosphere and outer space. This layer can extend thousands of kilometers above Earth's surface.